Okay, let's get to this interesting problem of optimization. Optimization is where you want to maximize or minimize something. So in this case, we're trying to maximize or minimize this, what we call objective function, using these limitations or constraints. Okay? So the idea is your objective function depends on an x value and a y value. We want to find the x-y combinations that maximize and minimize this p-value calculated by 10 minus x minus y. So to kind of show you that, I've made an animation here. So I made this animation using a program called GeoGebra. And so the idea is, if you look at those inequalities, let's go back to OneNote here. If you look at these inequalities, these limitations, these constraints, if you graph those, you typically will get a region of overlap on the plane. So in GeoGebra, you might get something like this triangle, okay? So these are your limitations. And so if you consider that in 3 dimensions, it looks something like this. Let me see if I can get this to do what I want it to do. There we go. So you can see now our triangle, our limitations from our inequalities are here on the xy plane, and now you've got a z dimension going up, and the xy plane is kind of like a floor. All right. Now the objective function, which in the problem we're looking at is this p function, depends on x and y. We won't really get into this much, but if you were to graph that, it would actually be a plane. So it might look something like this green plane, and I can kind of show you what that looks like here by spinning this around. So you can kind of get an idea of the perspective of this thing. So there's your objective function here, indicated by this plane. Now, what I want to do is maximize the value of this plane according to these constraints. So what I can do is project this polygon, my restraints, my feasible region is what this is sometimes called. I can project my feasible region up onto this plane, and let me show you what that looks like if I were to do it. I'll turn on my projection polygon here. Hopefully that'll work. There we go. So now I've got a projection of this polygon onto my plane. So let me spin that around a little bit so you can see it. Okay, so you get an idea. If you look from underneath, you will see that it's an exact projection up through the xy plane of the polygon. Okay, and then what you can tell is that the maximum and minimum points actually do occur at the vertices of your feasible region. So the highest point on our plane, the maximum point on the plane, is this point up here. It's at a vertex. And the lowest point on the plane is this point down here, also a vertex. And so let me grab a screenshot of this and I'll put it back into our notes here. So let me summarize that now. Here's the general idea for maximizing or minimizing, or you could say optimizing, an objective function. Okay? So down here at the bottom, you get your feasible region, from the system of inequalities. Okay? And then up here, this plane is the graph of the objective function. So if we project our feasible region onto our objective function, we get this polygon, and what we can see is the maximum occurs at a vertex, and we can also see that the minimum occurs at a vertex. It does not occur anywhere else on the boundary or from the interior of the feasible region. Okay? So the point is, of all this, we need to find our feasible region, determine the vertices, test them to maximize or minimize objective function. Okay, so that's what we're going to do. So let's go back to the original problem and apply this concept. All right, so the first thing we're going to do is use our inequalities to get our feasible region. Okay, so I'm going to take each equation, 2x plus 3y is greater than or equal to 14, and then I've got x minus y is greater than or equal to negative 3, and finally 4x plus y is less than or equal to 18. I'll put each of those in slope-intercept form. So there's the first one. Divide both sides by a negative, which flips the inequality symbol. And last is easiest. So we've got our three inequalities in slope-intercept form. Now we can graph our feasible region. Okay? So let's plot these guys. So the blue boundary line has a y-intercept of 14/3, which is a little bit more than 4. 1, 2. Actually, I'm looking at the green one. I can see I've got a y-intercept of 18. So I'm going to go ahead and mark up to 18. Which is up here. And has a slope of negative 4, so I'll rise negative 4, 1, 2, 3, 4, and I'll run 1. So I'll have this line first. Let me label that. My boundary line is negative 4x plus 18, and since it's less than or equal to, I know I'll shade below that line. Okay. Now let's do the blue line, which has a y-intercept a little bit bigger than 4, so 1, 2, 3, 4, and a little bit more. 4 2/3 precisely. And my slope is rise negative 2 and run 3. So 1, 2, and then 1, 2, 3. So my blue line looks something like this. And that's y equals negative 2/3 x plus 14/3. And since it's greater than or equal to, I know I'll shade above that line. Finally, my red line has a y-intercept of 3, which is here, and a slope of 1, so I'll rise 1 and run 1. And I get a line that looks something like this. Okay? And since it's less than or equal to, I need to shade below. So when I consider the overlap of all three of those, above the blue, below the green, and below the red, my feasible region is what I have highlighted there in yellow. And then I need to know my vertices. Let's call this vertex A, this vertex B, and this vertex C. So let's find my vertices. So for A, I know that that's where the red and green lines meet, so I know y equals x plus 3 from the red line. And from the green line, y equals negative 4x plus 18. So I need to solve this system. Easiest way is to do it by substitution. I know that y is x plus 3, so I'll plug x plus 3 in for this y. X plus 3 equals negative 4x plus 18. Let's solve for x. Add 4x over to get 5x, and subtract 3 over to get 15. Divide by 5, and we see that x is 3. If I plug 3 back in to either one of these, let's plug it into this one. Sorry, drew my arrow to the wrong x. Plug 3 in for x, I see that y is 3 plus 3, so y is 6. So A, our vertex A, is the ordered pair 3, 6. So that's one vertex. Let's find vertex B. B is where the green and blue lines cross, so the blue line is y equals negative 2/3 x plus 14/3. And the green line is y equals negative 4x plus 18. Let's solve that system now. Again, substitution. Maybe I'll plug this in for y over here. I don't like the fraction, so I'm going to multiply both sides by 3 to give me negative 2x plus 14 equals negative 12x plus 54. Now I trust my arithmetic a lot more. Add 12x over to negative 2x, giving me 10x, and subtract 14 over from 54, giving me 40. Divide by 10, and we see the x is 4. And then I'm going to plug 4 back in for the x on this equation so I can avoid the fractions of the first. So I can see that y equals negative 16, negative 4 times 4, plus 18, so y equals 2. So the vertex B is the ordered pair 4, 2. Finally, vertex C. C is where the blue and red lines cross, so the blue line is negative 2/3 x plus 14/3, and the red line is y equals x plus 3. Substitution, surprise, surprise. So we've got negative 2/3 x plus 14/3 equals x plus 3. Multiply both sides by 3 again to avoid all those fractions. Right, I just distribute my 3 here. And on the right side I've got 3x plus 9 when I distribute my 3. So I'll add 2x to give me 5x. I'll subtract 9 to give me 5, and I can see that x equals 1 when I divide by 5. And then I'll plug 1 back into this equation for x to see that y is 1 plus 3, or y is 4. So the vertex C is the ordered pair 1, 4. So now I've got my 3 vertices. So my vertices are the ordered pairs 3, 6, 4, 2, and 1, 4. I know these are the only candidates to give me my maximum or minimum values of P. Remember, P equals 10 minus x minus y. And we want to maximize and minimize this. So I'll plug in 3 and 6. I'll plug in my first order pair, 3 and 6. So I've got 10 minus 3 minus 6, which gives me 1. So P is 1. Let's write this a little better. So if I plug in 3, 6, I get P equals 1. If I plug in 4, 2, I get P equals 10 minus 4 minus 2, which is 4. And if I plug in 1, 4, I get P equals 10 minus, minus 1 minus 4, which equals 5. So we can see that 1 is the minimum value, and it occurs at the ordered pair 3, 6. So P is 1 occurs whenever we have the ordered pair 3, 6. And then the maximum value of the objective function is 5. So 5 is the maximum value at the ordered pair 1, 4. Lots of ways to word this. It just depends on the instructions. But we've got our minimum and maximum values and the ordered pairs where they occur. Okay, so here it said find the maximum and minimum values. We did that. Those are our values 1 and 5. And we went a step further by telling where those maximum and minimum values occur, what ordered pairs output those maximum and minimum values. Okay, so I hope this has been beneficial. Good luck on your own.